Welcome students again. Today we are going to discuss certain properties of factor rings. And yesterday we ended up with some notes or questions that when we have some quotient ring, then when this ring, it is natural to ask that when this ring is going to be a field or when this ring is going to be an integral domain. Because in general, the integral domains and fields, they have very interesting properties. And they are all defined. These factor rings are defined with the help of what we call that ideal. Okay. Before starting the main thing today, I don't know if I told you about principal ideal. I think I gave just a brief thing about principal ideal, but let me make it clear that what we mean by principal ideal. Okay. So in this way, we will be having a prime ideal, maximal ideal, as well as the principal ideal. Okay. Actually, principal ideal has the notation similar to that what we keep in case of the cyclic ring, cyclic group. Okay, but the operation and structure is something different from that that cyclic notation. Okay, so and also the when we are defining what we call that principal ideal, the rings should be commutative and having unity. Okay, and that this thing you can see in your book in chapter number 14, example number 3. Okay, chapter number 13, 14, chapter number 14, and example number 3, I guess. Okay, so in this you can see the proper definition of a principal ideal. Okay, but for the sake of completeness, let us see. So we can say that R, where R is a ring. Okay, let R be a commutative ring. With unity. And you know that in other cases, we never assumed that, okay, this should be having unity. Okay, in case of principal ideal and maximal ideal, we were assuming only this commutativity. Okay, we were assuming only commutativity in case of a principal ideal and maximal ideal. But here, in case of in case of a prime ideal and maximal ideal, okay, we considered only a commutative ring. But here, in case of a prime this principal ideal, we need to consider R is a commutative ring with unity. Okay, so let R be a commutative ring with unity, and let A belongs to the ring R. Okay. Then the set A, this is generated by RA. Okay, this is a collection of elements of this form RA, where R belongs to capital R, is an ideal. Is an ideal of R and is called the principal ideal. Principal ideal. So where if we compare this in a group, so in group we used to write we used to denote this a cyclic group like this. Okay, so in that case we used to write, okay, in this element will be of the form like this. Okay, or this will be collection of the elements of the form like this. A belongs to Z. Fine. A belongs to G. So this need to be taken care. Okay. So here in a ring, when we are writing like this, there is a different meaning. Of course, in additive group, we used to write n times a. But here, okay, this n is an integer. But here, in case of the ring, when we are considering principal ideal, this r should be a member of the ring. Okay. Fine. So these things need to be taken care, and this is an ideal. You can verify it, or you can refer maybe, I don't know, in your book it is not there, but still you can try. Okay, it's very easy to prove that this is an ideal. So you need to just take R1A and then R1 R2A. Okay, and then you can take what do you say that. Uh, Okay. One more thing, because you know that, okay, here you can take a common, so R1 minus R2, okay, this is going to be A. And because R is a ring, so this is going to be a member of R. So this is going to be some R A, okay, and this is going to be in this, okay, this is going to be a member of like this, okay, because R belongs to capital R. Fine. So likewise, you can try it for product also. One more thing I would like to tell you that either you write it like this, R A and R belongs to capital R, or you can write this as also A R, where R belongs to capital R. You know, and this is because of commutativity. Fine. This is because of commutativity. So in both the cases, proof will be similar. If you want to prove that this set that's generated by A is an ideal. Okay. So with this, I am ending this note here. So let us proceed for further example. And yesterday we were talking about some quotient or factor ring. Yeah, we were talking about factor rings, and we have seen some examples. And the example, uh, I don't know whether we have considered this or not. I don't remember. But you see that there are elements like 40 plus 4z, and then 1 plus 4z. All right, and 2 plus 4z, 3 plus 4z, like this. Fine. And essentially, this is nothing but this is going to be our Z4. All right. This is Z4. I mean to say that they are not equal, but they are it is isomorphic to Z4. Fine. Here, when we are adding 0 to every element of 4z, you know that it will be 4z only. Okay, it will be 4z only. Then 1 plus 4z you will be getting. So this will, when you are reducing it under multiplication modulo 4, so you will be getting 1 here, 2 here, 3. So essentially you are going to get Z4. Fine. And similarly, I think we have also seen another example, 2z by 6z, this quotient, okay, this factor ring. And in this, there are three elements, 0 plus 6z, and 2 plus 6z, and 4 plus 6z, like this. Right? So there are three elements. So size matters. The size of this is 4, and the size of this is 3. Okay. Another example, I think there is another example, example number 10 in your, you can, example number 10, you can try it out. Okay. This is on matrices. But example number 11 or so, there is a interesting example. So I would like to quote this. Okay, consider this is, I don't know, this is example number, but in chapter number 14. Okay, chapter number 14, you can see. Consider the ring. Okay, in fact, factor ring Zi. Okay, and you know that 2 minus psi iota, and this is going to be a principal ideal. Okay, this is going to be the principal ideal in Zi. So we can talk about the factor ring. Okay, this is a factor ring. Factoring. So now question is that what about the structure of this ring and what kind of elements we are going to have here? Okay, fine. So definition says that here the elements will be of the form. You take this one 2 minus iota, okay, and then take elements from here iota, okay. So there will be elements like this a plus ib, okay. So such that a plus ib they belongs to zi, and you know that a and b should be from integers, okay. So actually, this is by definition. Uh, this will be the complete set of okay. But question is that how many elements will be there and how we can reduce them. Okay. So this need to be answered. Fine. So you know that. When you are adding, because you know 2 minus I, okay, this is by definition is this going to be have member of this type a plus ib, something like this, okay, or you can a1 plus iota b, okay, b1, because I have used here, okay, and then you can multiply it to 2 minus I like this, fine. So a1 plus iota b1, this is going to be a member of zi, okay, this is going to be a member of zi. So here we see that what type of structure this set has. Hmm? But how we are going to simplify, that is the question. Okay, that is the question. So here in this case, if you see that every element is a multiple of 2 minus I. Every element is a multiple of 2 minus I, and which multiple is this a multiple of elements of ring, the parent ring Zi. Okay. So now let us consider some case. If I write 2 minus I and plus 2 minus I, okay, for example, if we consider this, okay, and because 2 minus I is nothing but this is a multiple of 2 minus I, and of course we can write it as 1 plus iota 0, okay, 2 minus I plus like this 2 minus iota. Fine. Are you getting what I'm trying to say? You know, this factor becomes 0, so 1 times this one, and this you know that 1 and 0 belongs to zi, z. So this is going to be a member of zi. Fine. Okay. So in this case, it means this is going to be absorbed here because this set is a multiple of 2 minus I. So this should be a member of this set, no? This should be a member of this set. And when we are adding this element to this will be absorbed. Okay. And also this is because this is an ideal. Okay. You know, in ideal, because this 2 minus iota, this is an ideal. So this will be left ideal as well as right ideal. So RA and AR should be member of what? This 2 minus I. Fine. This should be member of I. So when either we multiply this times this or this times this, they both will be in uh, in in this set, in this set, okay, in this set. So certainly this is going to be equal to, because then this, if this is going to absorb here, if this is going to absorbed here, it means what? This is going to be 0 and this is going to be absorbed, that is going to be here. So what we have, we can write like this. Are you getting what I'm trying to say? Hello? 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 Is anyone there in class?
Yes, sir.
So why you people are not responding? I don't know if I'm connected or not connected. Is there any network problem? At least you can say yes or no, something. At least you can say like this. But anyway, what could be done? So this means what? This implies that 2 minus iota, this should be 0, and this holds if 2 equals to I. So this is interesting, something amazing. 2 is equals to I. Okay. So now we can consider the example 3 plus 4i, and when we write 2 minus iota, this is going to equal to 3 and plus 4 times 2, and then 2 minus iota. Okay, so 3 plus 8 and uh, this 2 like this. So 3 plus 8 11, and then 2 minus iota, we can write like this. Nah, we can write like this. So a 11 is there, 11 plus this set. Okay, but can we reduce it further? That is the question. Okay, can we reduce it further? This is the question. Okay, so this yeah, this can be reduced. For this, let us consider now, since you know that 2 equals to I, so this implies what? 4 equals to negative 1. Interesting. This implies that 4 plus 1 equals to 0, and this implies that 5 equals to 0. Ah. So we have 5 equals to 0. So this expression 3 plus 4 iota and plus 2 minus iota, this is going to be 11. We can write 1 plus 5 plus 5 plus this. Okay. So each 5 is 0. So we are left with the 2 minus iota, 1 plus 2 minus iota, like this. Okay. So this is the simplest form we can have of this expression. Okay. Okay. So now in this way, uh, when we consider z I, this factoring. So what are the elements here? Okay. So what we are seeing in this case, that when 11 is coming and 5 becomes 0, 5 is equivalent to 0. So when we are dividing it by 5, okay, like this, so we will be getting remainder 1 in one sense. Okay, that is, we are talking about the modulo division by modulo multiplication, division modulo 5. Okay, division modulo 5, or else uh, of course by after addition. So here we are adding, here we are adding. So when we are adding and uh, taking the division with the modulo 5, we are getting 1 here as a remainder. Okay, so what are the possibilities for elements here? So either we can get a remainder 0. Here we are getting remainder, na? So either we can get remainder 0, we get remainder 1, we get 2, we get 3, we get 4. Okay, like this. We can get uh, any of these 5 possibilities. Okay, so what are the elements here? So we can have 0, 2 minus I, 0, 2 minus I, sorry, 1 here, 1, okay, then 2, and then like this. There are other two elements, 3, 2 minus iota, and 4, 2 minus iota, like this. Okay. So these are the possible elements we have here. Okay. So thing is that none of them are equal. None of them are equal. Because in case if they are equal, then we have certain possibilities that I'll tell you. There are exactly 5 elements. Okay. Acha, can you tell me this is isomorphic to which group, or yeah, which group, or equivalent to which group? Do you have any answer by looking at the structure? Hmm? Hello. No. Okay. So this is a question, but the thing is that you can think of something like this if you find it out. Okay. So again, they are actually different. Okay, they cannot be equal. They cannot be equal. You can see the example of your book. It is given in your book. Okay, let us take another example, which is also going to be interesting one. So next example is that let Rx denote the ring of polynomials with real coefficients. With real coefficient, and let x square plus 1. Of course, this is a polynomial, and according to the definition of principal ideal, this is going to be a and this is going to be the principal ideal. Denote the principal ideal generated by x square plus 1. Generated by x square plus 1. That is, you know that x square plus 1, this contains the element of the form fx, x square plus 1, where fx is any polynomial. For each polynomial, fx belongs to Rx, like this. Okay, so this is the principal ideal generated by x square plus 1. And then we can talk about the quotient ring Rx. Okay, Rx by x square plus 1, the ideal generated by x square plus 1. And you know the elements in this are going to be of the form x square plus 1. Okay, and here we can write some gx. Okay, here we can write some gx, and yeah, we can write here gx, where gx is a member of Rx. Okay, the polynomial, any polynomial with the real coefficients. Okay, so this is the structure. So the question is that how we can reduce it, you know, and here gx is any polynomial with the real coefficients. Okay, so in a similar way, if we have this principal ideal, we can divide this gx by x square plus 1, So what is the possibility for remainder? Okay, we can write this gx as when we are dividing this gx with uh, gx by x square plus 1, we can write some qx into x square plus 1. Okay, this is the quotient, and plus rax. Okay, so you know that in case of rax, either we have rax equals to identically 0, okay, or degree of degree of Rx is less than or equals to 1, you know, because if it is a 2, degree 2, then again we can divide it by x square plus 1 to have some remainder. Okay, so this is the case. Fine. So this gx is equivalent to and one more thing that because this is a principal ideal is generated by this element, and so any multiple with the element of ring, this will absorb in the ideal. Okay, qx and x square plus 1. This is going to be member of x square plus 1, certainly. Okay, so therefore we are left with this only. Okay, so therefore gx plus x square plus 1, this element is going to equal to rx, and here x square plus 1, like this. Fine. So and one more thing, we can have some example here. You see, in some particular case, if you are talking about x square plus 1 and plus we are taking x square plus 1, right? So because this is a member of this set, so we are going to get 0 plus x square plus 1. All right. And this means that x square plus 1 equals to 0. And this implies that x square equals to minus 1. X square is minus 1. Okay. So for instance, if you take, let us consider x plus 3. Let us talk about the product x plus 3 and x square plus 1. This is a member, this is a polynomial of degree 1. Okay, so this member, let us multiply this with another 2x plus 5 plus x square plus 1. Okay, with this. So as a usual multiplication, x times 2x, we are going to get 2x square, and then plus 3 times 2, that is 6x plus 5x plus 15, and plus we are going to get x square plus 1. Okay, because in case of ideal is going to be ideal. Okay, so when multiply, because ideal is closed. Okay, so let us write it 2x square plus 11x plus 15, and then the principal ideal we can write. Okay, now since x square is equal to my negative 1, so what we have here, minus 2 here. Okay, so minus 2 plus 11x plus 15 plus this. This implies that 11x plus 15 minus 2 is what, 13, and plus x square plus 1, x square plus 1. So this is the simplest simplified expression we have. Hmm? This is the simplified expression here. Okay, so actually this is of the form ax plus b plus like this x square plus 1. Nah? Okay, so either if a is 0, then it becomes constant. If b is 0, then it becomes ax, and if a and b both are 0, then it becomes 0. Fine. So this is the form here Rx can take. Okay, so Rx degree less than or equals to 1. If it has degree 1, okay, then it will be of this form like this. Okay, this is of degree 1. Okay, fine. Or there are two possibilities. Even exactly you can write like this, exactly less than or equal to 1. Either its degree is 1. Okay, either Rx is 0, Can we have degree 0 also? Yeah, we can have degree in case of constant, no? In case of constant. So we can write like this. In case of constant, that is if Rx equals to B, so we can write like this. So in this case, degree becomes 0. Okay. In case B is not 0. Fine. So let us move further. There are two results that I would like to mention. This is from your book. So this result says that let R be a commutative ring with unity. Commutative ring with unity, and let A be an ideal of R. Note that we are taking commutative ring with unity. Okay, and A is an ideal of R. Then the factor ring R by A is an integral domain if and only if A is prime ideal. Okay, so and next theorem says that it is talking about the maximal ideal. Okay, uh, so in case A is prime ideal, so R by A becomes integral domain. In case A becomes maximal ideal, so R by A will become a field. Okay, so that is given in next theorem. So let R be a commutative ring with unity, commutative ring with unity, and let A be an ideal of R. Then the quotient ring R by A is a field if and only if A is maximal. A is maximal. Okay. So in order to R by A, this factor ring is to be a field, A has to be maximal, and conversely. And if in order to be R by A, this factor ring is to be an ideal, integral domain, A has to be a prime ideal. Okay, so the difference between these two results are very much clear. Okay, very much clear. Let us see the proof of the first one. One more thing I would like to point out that why we are here the consideration of unity, okay, commutativity and unity plays the role. Okay, plays the role. Here we are not considering only R is a commutative ring. Okay, but here we are considering that R is to be commutative ring with unity. And you should note that while defining integral domain, we considered that R need to be a commutative ring with unity. Okay. Okay. So let us see the proof. Let me write. This is the number one. Okay. Here, number one. This is 2. In your book, there are different numbers for these theorem. Okay. So let us suppose that R by A, this factor ring is an integral domain. Is an integral domain, and AB belongs to A. Okay. So what we need to prove? We need to prove that A should be capital A should be prime ideal. So if A and B belongs to A, or let us write like this. Okay. Suppose R by A is an prime ideal. Okay. So what we need to prove? We need to prove that A prime is prime ideal. Okay. So to prove that prime ideal, we need to refer the definition. If A, B belongs to I, ideal I, this implies that either A belongs to I or B belongs to I. So in this case, we need to consider that A times B belongs to A, and then we need to prove that either one of them is going to be a member of A. Okay. So now suppose that A plus A and B plus A. Okay, these are, you know, that they are elements of R by A. No? Or let me write like this. A plus capital A and B plus capital A belongs to R by A. Then uh, we can have A like this. Okay, and then take product B plus A. So by definition, this is going to be AB. Fine. AB plus A. Okay, this is going to be R by A is an integral domain. Okay, this R by A is an integral domain. Okay, so let us write here. You know that zero element of R by A is nothing but A. Okay, okay. Not then let. Okay, A should be zero element. Okay, zero element of R by A. Fine. And in the left side, what we have? In the left side, we can write A, B plus A. A is given as ideal, you know, but it is not prime ideal. We don't know about this. So A times A and plus AB plus A. This is equals to A. Fine. And this implies that AB plus A equals to A, as A capital A and AB belongs to A. Why? Because A is an ideal. Okay. So this implies what? This implies that uh, okay, A times B. Okay. So here, because A and B are members of which A and B are members of R. You know, A and B are members of R. So this is in fact this is equals to what? This is equals to A. Okay. So in total we can write A plus A and B plus A. This is equals to A. So what we have, this implies that A plus A equals to A, or because this is zero element, capital A is zero element, or B plus A is equals to the zero element, that is A. Okay. So this means that either A belongs to A or B belongs to A. Okay. The converse part is that if we consider conversely, let let A be prime ideal. Okay, prime ideal. Then we claim what we need to claim. We need to claim that R by A is an integral domain, and this is happening because this is happening because A is an no, R by A is an integral domain by assumption. No? So we are assuming that A is a prime ideal, so we need to prove that this is an integral domain. Okay. So in integral domain means what? We need to prove that there should be no zero divisor. Okay. There should be no zero divisor. For this, we can consider A plus A and B plus A times B plus A. This is equals to, okay, this is equals to A, that is zero element. This is equals to zero element. Okay. So the left hand side, what we have, A B plus A equals to A. Okay, in the left hand side, because A is an ideal. So this means that AB belongs to A, and therefore either A belongs to A or B belongs to A. A belongs to or B belongs to A. Okay, fine. So this means that one of A plus A, this means that either A plus A or B plus A is the zero element of R by A. Okay. So this completes the proof of the result. The next proof of the next theorem we will be doing tomorrow.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.